Welcome to this explainer where we're going to take a dense, incredibly intimidating textbook chapter of calculus theorems and transform it into a simple, easy-to-remember toolkit for finding derivatives. Honestly, if you've ever felt completely overwhelmed by the sheer number of formulas in calculus, you're exactly in the right place. Today, we're zeroing in on how to effortlessly recall the derivatives of algebraic, trigonometric, logarithmic, and exponential functions. And we're going to lock these into your brain not by boring rote memorization, but by uncovering their hidden core patterns. Okay, let's just dive right into it. Think about the Hennessy Venom GT for a second. Back in 2014, this beast reached a record-setting speed of over 270 miles per hour, literally going from 0 to 200 in a mind-blowing 14.51 seconds. Now, calculating the exact instantaneous acceleration of that car at any given split second of its run, you absolutely need derivatives for that. They're the ultimate mathematical tool for finding the instantaneous rate of change. But trying to calculate that the foundational way, it is incredibly exhausting. You see, this right here is the difference quotient. It's the mathematical bedrock of all derivatives. It calculates the slope of a secant line between 2 points, and then, by using a limit to bring those points infinitely close together, boom, we get the exact slope of the tangent line. And yeah, conceptually, it's a beautiful thing. But frankly, if we want to survive calculus without writing pages and pages of tedious limit proofs every single time we need to analyze a moving car or a growing population, we need shortcuts. We really need a toolkit. So, our agenda for today is simple. First, the basic rules. Then, trigonometric patterns. Third, exponentials and logarithms. And finally, the ultimate multi-tool. Let's get into it. Starting off with part 1, algebraic and basic rules, the building blocks. Instead of setting up a massive limit equation every single time, we're going to rely on these foundational algebraic shortcuts, the constant multiple rule, the sum rule, and the difference rule. And they are brilliantly intuitive. The constant multiple rule just tells us that if a function is multiplied by a constant, you literally just pull that constant out, take the derivative of the function, and multiply it back in. Easy, right? And the sum and difference rules, they just mean that if you have a massive string of terms added or subtracted together, like your classic polynomial, you do not have to panic. You just calmly take the derivative of each individual piece, one by one, and add or subtract the results. You're basically taking big, intimidating algebraic problems and breaking them down into bite-sized, totally manageable pieces. Moving right along to part 2, tackling trigonometric functions and their cyclic patterns. So it's pretty wild how the visual shape of a wave can bridge the gap to a hard mathematical rule, especially when we're dealing with trigonometric functions that dictate simple harmonic motion, like a pendulum swinging or a weight bouncing on a spring. Just look at the classic rolling wave of the sine function. If we calculate the approximate derivative of that sine wave, mapping out its rate of change at every single point, we get this incredible match. Notice anything familiar? The graph of the sine function's derivative perfectly mirrors the shape of a cosine curve. Wherever the sine graph hits a peak or a valley, a horizontal tangent, its derivative crosses exactly through 0. This visual perfectly bypasses all that long difference quotient math and proves that the derivative of sine of x is simply cosine of x. The absolutely crucial takeaway here is that you don't need to memorize 6 random disconnected formulas. To effortlessly lock these 6 trig rules into your memory, just look for the defining linguistic trait. Check out cosine, cotangent, and cosecant. What do they all have in common? They all start with the letter C. They're the co-functions. And if you look closely at their derivatives, every single one of them, and only them, results in a negative derivative. The derivative of cosine is negative sine. Cotangent is negative cosecant squared. Cosecant is negative cosecant times cotangent. If the trig function starts with a C, its derivative gets a minus sign. It's literally a flawless memory hack. Okay, on to part 3, exponentials and logarithms. I like to call these the invincibles and the rescalers. Let's say we have a mosquito population growing exponentially. It's a terrifying thought for sure, but a mathematically perfect scenario for applying these rules. If our population is represented by a function like a of t equals 1,000 times e to the power of 0.3t, and we take the derivative of this to figure out the instantaneous rate of change, basically how fast those mosquitoes are multiplying on any given day, we find a stunning quirk. The ratio of the population's rate of change compared to the total population itself is always exactly 0.3. The rate of growth is perfectly proportional to the current size. That right there is the defining magic of the natural exponential function. Honestly, the absolute easiest way to memorize the derivatives for these natural functions is by contrasting their ultimate behaviors. Just look at the sheer invincibility of e to the power of x. It is the only function where its derivative is exactly itself. The derivative of e to the x is just e to the x. It's indestructible. Now contrast that against its inverse, the natural logarithm of x, or ln x. Logarithms are the ultimate rescalers. They take massive exponential numbers and bring them right back down to earth. Fittingly enough, taking the derivative of ln x transforms it neatly into this incredibly simple algebraic fraction, 1 over x. So you've got invincibility on one side and beautiful simplicity on the other. Finally, part 4, the ultimate multi-tool, logarithmic differentiation. All right, so we have our basic rules, we've got our trig patterns down, and our exponential shortcuts. But what actually happens when we face monstrously complicated equations with variables jammed into both the base and the exponent? Well, that's when we pull out our ultimate multi-tool, logarithmic differentiation. This is a super simple 5-step strategy that uses the properties of logarithms to absolutely dismantle massive problems. By taking the natural logarithm of both sides of a complex equation right from the start, you can use log properties to drag those stubborn exponents down into simple multiplication and break messy division into straightforward subtraction. Suddenly, an unsolvable nightmare becomes just a string of basic sum and difference rules. You differentiate both sides implicitly, multiply your original y back over, and boom, you're done. It's the ultimate workaround. It turns the hardest calculus problems into basic algebra using the exact toolkit we just built. As we wrap up this explainer, I really want you to take a step back from all the formulas for a second and just think about the history here. What must it have been like for the absolute pioneers of calculus? Guys like Isaac Newton, who, by the way, arguably developed his best foundational calculus work while quarantined during the Great Plague, and Gottfried Leibniz. How did they feel when they first recognized these beautiful, hidden shortcuts that govern the universe? Just imagine the sheer awe of realizing that the chaotic growth of nature, or the incredibly complex motion of planets, boils down to these elegant, totally predictable rules. When they first started figuring this stuff out, they had to rely entirely on those tedious, exhausting secant lines and complex limits. Every single calculation was an absolute mountain of work. But now you have a fully organized mental toolkit. You know that constants simply pull out, cofunctions are always negative, e to the x is totally invincible, and logarithms can dismantle literally any algebraic nightmare. You can bypass the long way and instantly uncover the mathematical secrets of the world. Which leaves us with one final thought to ponder today. If these surprisingly simple mathematical shortcuts perfectly describe the incredibly complex, chaotic universe around us, what other universal secrets are out there, just waiting to be distilled into a simple pattern?